All right, so my name is Samuel Fournier. I'm the co-founder and CEO of Crystal Labs. We're a soil carbon MRV company based in Montreal, Canada. So we have developed an optical design sensors to look at soil, and we basically support the industry with primary data for carbon quantification. So today's topic will be about soil carbon MRVs. We'll listen to different panelists that will share their vision about the market today. So I have a little intro here that I need to give you. So it's giving the growing importance of soil carbon sequestration to reach the climate objective that we have to comply with the private sector decarbonisation strategies. We need to have transparent ways to do MRV. So MRV stands for measurement, reporting, and verification. So most of the people that you'll hear today will talk about these three letters. Some will talk about specific letters. Some will talk about all these letters. So you'll hear people talking about remote sensing. You'll hear people talking about proximal sensing. You'll hear people talk about the different schemes that also exist within the industry here in Europe, specifically in Germany, and across the world more broadly. So it is a pleasure to have all of you here discuss about the industry, because if we're not able to properly monitor and quantify carbon specifically in the VCM market, then there's no value of the assets we're creating. So we need to be very thorough and put a lot of science behind how we're looking at the data properly to make sure that we can account for a specific done. So today's we'll have 6 different presenters, so about 15 to 20 minutes each, and this will be followed by a Q&A session, so all the questions will be at the end, like every single panel that we had since yesterday. So the first speaker is Professor Dr. Bruno Basso. So he is an ANA Distinguished Professor, Art and Environmental Science at Michigan State University. And today he'll talk about modeling net climate benefits and dynamic baseline of regenerative practices.
Okay. Well, a pleasure to be here. I'd like to thank the organizers for inviting me to share with you the latest work that I'm doing. I was actually asked to talk, as you can see, a lot of different title. I mostly focus my work on modeling and remote sensing, so geospatial modeling, but I have had exposure to all the components of the MRV. So I'll really share with you some of the direct experience that I have in measuring and monitoring, as well as to finally reporting the quantification of soil carbon. In general, you'll see that I focus more on net climate benefit, because we cannot ignore nitrogen, even though the talk is on soil carbon, but you gotta consider the system. That's a very critical outcome you should walk out with. So the good thing about coming a little bit later in the conference is that I don't need to spend much time on the value and the importance of why we need to sequester carbon. So I'll move rather fast here for all these benefits, very well known to all of you, in addition to the climate solution, potentially contributing to climate solution. One thing that I think it was really maybe clear to me, that there is a misunderstanding on the type of carbon schemes and offset versus insets. So I just wanted to share that. The offsets is basically like a share, right? You can resell it. It has complexity behind, significantly much more than a farmer could even take on. In fact, in the US, they have not taken off at all, because of the problems related to additionalities. A lot of the farmers, for the first year in the US, we have more acreages under no-till than any other of the tillage system. So it's very important. Europe is incredibly ahead of the game in driving policies, but the no-till application or in general reduced tillage in Europe is 5%. Versus 40% or 95% in Argentina or Brazil. So something is disconnected, what a farmer would like to see, on their farm versus what they potentially could be doing better in a way. So additionality, permanence, it's really complicated. Takes time to build carbon. So offset and permanence, the contracts are signed for an average of 30 to 50 to 100 years. I have never met a farmer that it was, kind of willing to sign a contract that they will not till back in the next 30 years. They said, I don't even know what I'm going to plant next year. What is very popular instead in the US are the insettings or the equivalent of Scope 3 emissions. So as Francesca said, I need to do also disclosure. I have co-founded a company, on the scientific side, investors, high-profile investors invested in SIBO Technologies, which is the back end of many food companies, CPGs, in delivering the quantification of soil carbon through modeling, so a verified through Vera registry model. And so the Scope 3 emission, it's really what has been more popular, and it's basically acquiring the procurement of a better way of managing your ingredients, basically, that quantifying the emissions reduction coming from the food that goes into the products that they sell. So I was asked to, again, share some of the complexity, and so I have had publications in all the system that you see there. And I know, especially knowing, my colleagues following, that there are lots of novel solutions that would improve some of these limitations. But laboratory procedure, sampling strategy, bulk density, remote sensing and spectroscopy, promising technique, process-based model. And what we're really working now, going towards the future, is basically training systems through process-based models. So one of the first high-intense, typical, kind of research site, sending the same samples, 36 the same samples, to 4 different laboratories. So first you see the agroforestry, all different type of management on this farm, very large variability within all those points, the blocks there that you see. And the 4, the TC1, 2, 3, and 4s are the results from the same soil, the same exact soil, from 4 different labs. When you quantify the type of changes, what you get is from 1% to 1.2% to 1.4 or so. But unfortunately, it equates, and those are the same ranges that you see within the spatial variation. So as you can see, from 54 to 61 or so, 7 to 8 tons differences that, if people realize how small is the change, that's like 10, 12 years of accumulation, just coming from 4 established laboratory. And none of these numbers you would say is necessarily more correct than the other. They use different procedure. I mean, the procedure on paper, they're supposed to be the same, but the sievings that is done differently, the type of grinding and everything else. But anyway, we wanted to present. And what you see on the right, it's also a very detailed study by Evan et al. With Francesca Cotto, showing that level of differences just from the different laboratories as well, in the context of different soil type and different methods. So that's one large level of, and we know Lucas uses one, laboratory in Hungary, which is backed up for the next, I don't know how many years. But the problem is that it isn't just the one single lab, is the human labor as well, machinery that will change, upgrades and new technology that would come in. Another thing about sampling, shown already with the previous slides, one of the things that we think it could be really improved is using plants as indicators of accumulation of carbon. So we had an hypothesis. We know across the entire Midwest of the US, corn and soybeans rotation, which areas are constantly performing well versus within field variability versus constantly what we call stable low productivity. So in the low and stable zones, we expect carbon to be lower, but not because obviously the plants don't take carbon, from the soil. It's just the properties and being exposed to, stress conditions. And so the low and stable zones sure enough, when we measured this transect, and Francesca has co-authored a paper together on this by partitioning the different fractions. But in general, one way of selecting where to take fields within, it's using plants as indicators of what has been returned over time. The other piece, again, that seldom is done correctly or accounted, it's basically the adjustment, the equivalence on mass of bulk density. So I can't be much more clear than a graphics like that, where the same size rod, it goes back 10 years later, where you have hopefully accumulated soil carbon. The soil has really kind of swollen because bulk density is lower, more air, better aggregates, more macropores, whatever, you name it. And then the rod is basically short by, it's not sampling the same volume. So adjusting for that, and basically the exponential function and decay that you have by soil organic matter decreasing by depth. So there is a correction factor and an Excel that is available from the paper that you can basically adjust the bulk density, knowing how much the equivalent soil mass. Basically, you know that you need to sample 33 centimeters rather than 30, or correct for it before you measure it. So the core of the talk that I really wanted to share is the role of modeling. So models have been around for a long time. They've been tested, and there are obviously a crude representation of reality, but we know the domain knowledge and everything that we have known, it's captured, they get improved over time. And so this is just an example of the pool sizes. Different models will have different approaches. This is one of the example of a paper, a large review that I wrote on how these models have been tested for what type of experiments, and the papers. So this is just for the DSET and Salus models, the model that I developed, where has been tested independently by independent researchers in maize, wheat, and soybeans across the world. These are the number of papers reporting measurements and simulated results. So what we did, the next level, as a result of an initiative that I started with colleagues Cynthia Rosenzweig, Jim Jones, AgMIP, Agricultural Modeling into Comparison and Improvement. I lead the soil initiative, crop rotation initiative. So we execute multiple models. The difference is that instead of having the different groups, we execute the models in the lab with one click. We run all these 8 models, and we run it at scale to be able to show there is a very strong message in the end of how this could be used as an MRV system. So this is the spatial extent, about 90 million acres. Comparing conventional tillage with no tillage. There is an intermittent, many other tillage treatment, but I'm focusing on this. Corn and soybeans, full nitrogen, corn with and without cover crops on both of the tillage system, and then with a reduced nitrogen, 75%. Before we embark into running models and we collected the most extensive literature existing where till and no till were compared at the same time. And so some of these measurements vary between, you can see the colors, 0 to 5 years, 5 to 15, 15 to 30 years, okay? And the models were validated, all of them. The models were ran uncalibrated for except basically making sure that they all started with the same initial conditions. Different models have different ways of doing pool sizes and so on. So that's a level of calibration. You can see there's a tendency of losing on a higher carbon, but that's basically what we got. In terms of comparing, is a one model better than running multiple models? Unfortunately, that has been shown many, many times already in the literature extensively, high-profile papers all around, and the runs of multiple models reduce uncertainties and provide a better understanding of the model structure. And so it's really the problem is, even if you have a good model in one site, that's we showed both in this paper, it just never performs the same. So you can't cherry pick your model. So if you have a model that you run in one area, and again, it will give you potentially a different results. So running all of them, it's very much like what the climate community did. They run 20 climate models in order, and that's, we see improvements in that. So we execute, again, all of them, and again to show the multi-model ensemble proved to be the best model all the time. So here there is no agenda. We wish there would be a model that would be better. And the models are not named for privacy, and be able to show that these are still all highly popular and known models, but the multi-model ensemble showed to be the best performer. So one point initially when I mentioned about understanding and creating baseline is a really important topic, and models are the only system that can really allow to account for counterfactual. So if you change from a tillage system, let's say conventional, to no-till, you do not know how conventional till would have performed in the next 10 years. And so if you think people maybe ignore this component, because it could, in dry places, it could be the case too, where you go really, you lose a lot of the carbon and no tillage does much better. But in some of the humid region, no till does not necessarily perform as good, and it can be the case 3, but conventional till may continue to lose. If you think of any innovation, let's say new genetics, and you wanted to compare how the new traits, you have to compare the new traits with the conventional trait on the same year where climate it was a factor. You don't compare the yield now with the yield of 10 years ago, when there was a different, even the soil was different back then. And so allowing to have a dynamic baseline, it really brings more rigor to the entire conversation, because you can really, and companies are very interested, even in case 3, to know the avoided emissions, that it was an opportunity, the cost of not doing something. So even if you convert, you don't accumulate, there's nothing we can do about it. If you are on a high organic carbon soil, you only have to worry about not losing that carbon, but there will be very little accumulation, versus a low initial condition where you all have a greater potential to accumulate soil carbon. So these are the stocks of the US. Some measure, some revise the sorghum. You can see the differences, and so that's what it was used. One thing is understanding stock, again, for climate mitigation, how much carbon is stored, and one thing is quantifying change. Change is very, very small, in the range of a few hundred kilograms per hectare over the 50 or 70,000 kilograms or 70 megatons. So with the baseline, a farmer could say, I am a conventional till person, I do maize and soybean, and I put fully fertilizer. I'm interested in adopting no tillage, but I don't want to do cover crop. So basically you run the baseline and you can tease out the component, the benefits of the no-till. You can be a conventional, staying conventional tillage, but you want to know the impact of cover crops. And as well, if you are in an area that is all no-till, that's your baseline, and you want to know what is the impact of cover crops. So you can do these dynamic baselines through the multi-models. So now you can physically click on any of the single fields that we run at field size and be able to get the differences. So this is summarized basically, if you see the carbon level, very good predictor of the potential accumulation of soil carbon. So let's say you look at the no-till up there in the sandy soil with cover crop. If you have low initial carbon to start with, you have greater probability of the accumulation. If you are in another, if you were to be on high level, the darker spot, the same exact type of soil under no-till, you would not have the same amount of sequestration. So these are basically 80 million acres synthesized across latitude, climate, soil, just a good way of synthesizing. But you see the amount of carbon soil change on average for 30 years annually and annualized. It's in the range of losing to 300 up to gaining 200-300 kgs. So that's really the numbers. Now, moving faster and finishing towards the importance of considering, okay, you sequester carbon and then you put 300 kgs of nitrogen, you're far from being anything good to net climate mitigation. So here's an example synthesizing from this result. If you add cover crop to a no-till, you increase basically the N2O, but you don't have carbon sequestration. You further increase the net mitigation. You're much further in the first case. You can do better in the second case. But if you look at no tillage plus cover crop, you still have N2O emissions converted, into CO2 equivalent, and then sequestering 2.68, that leads to a net negative. And so that's basically the map of all these treatments, differences between this case from no-till plus cover crop minus conventional. So I want to say that trade-off is critical. We want increased yield, we want improved soil organic carbon, reduce N2O emissions, and they don't have necessarily the same, drivers. And so we're moving, Francesca mentioned about the importance of having integrated crop livestock system. We've been using the same approach and be able to quantify differences in soil carbon, greenhouse gas emissions in response to cover crops, crop diversity, including animals, reduced fertilization across the same system. I just want to finish with one important, possibly revolution that is happening in the US. This is a paper that was recently we published in the magazine of Science. And the multimodal ensemble could really be used to, this started from SAF, the Sustainable Aviation Fuel. As people that are familiar, they have an annualizing quantification of greenhouse gas emissions. They will access to the SAF market if they reduce the emission by 51% compared to petroleum. So taking advantage of that, farmers receive $200 per acre to basically move forward into reducing as much as possible the carbon intensity score. Currently, soil carbon is non-accounted. So we propose to further reduce carbon intensity score for any corn grower to basically for any use by adopting limited technology, conservation technology like no tillage, cover crop, variable rate fertilizer. And so this could potentially be a way of adopting with the same concept of annualizing how things are produced through a series of lookup tables that will give you how much carbon depending on where you are, what practices you do. You got to monitor to make sure that the practices are in place. Anyway, so we're working on creating API where all the models can be ran, and these are examples. I'll finish by saying climate smart, there's just no questions about the importance of increasing adoption because co-benefits. It isn't just about carbon. Annualizing carbon intensity score may increase adoption has already happening, even if you don't sell for SAF. And SAF, as you know, it's a CORSIA policy that in Europe, any plane landing in Europe has to have 20% of sustainable aviation fuel in the tank. And that's basically, we'll never have battery on the planes. That's the only way of decarbonizing aviation. So we can't measure everywhere, high uncertainty from such change, too costly. We have 100 million hectares of corn, wheat, and soybeans together. We sample, usually it's about $500 per sample. It costs $5 billion to basically sample one time. Obviously, you can reduce, as my friends will show next, but the cost is, who pays for it? That's a big question. Remote sensing is critical to monitor the adoption that is basically happening, and so that's actually pretty solved. We can detect tillage and cover crops from remote sensing. Models they don't need to be calibrated, or this is a game that often is done and it doesn't bring any use because the truth will eventually come out when you go to a next place. Models need to be tested independently. You have to have more of a circular, it's not just about producing soil carbon. Some models, some of the biogeochemical models, that's way off on yields. And so you question how they're going to return the carbon inputs. And so you have to have making sure that you reproduce all of those. Different variables, as I mentioned, spatial variation is important. Planes are great indicators, and multimodal ensemble through both potential lookup table provides an opportunity first to benchmark models, start understanding why a model does different than another, and the dynamic baseline are critical, reduce uncertainties, and potentially, again, through lookup table, you could basically revolutionize and greater adoption of a carbon farming scheme that is very much necessary. Thank you very much indeed.
All right. Thank you, Professor Basso. That was a very interesting discussion about modeling. So modeling is one of the most scalable way of looking at carbon in soil. So for those of you who are involved in carbon project or either in research, we see a lot of this in either measure and model approach. So there's a lot of this out there. And shifting gears, we'll look at another way to quantify carbon. So Julian Krimmers, the CTO of Secana, will talk about the MRV with remote sensing, opportunities and limitations.
Okay, maybe as we're trying to get the technology to work out, I want to raise a first question to you as the audience. Who here identifies as a... Now I missed the joke. You have to tell me after. Can I... Yeah, okay, perfect, thanks. Yeah, first question to you as the audience. Who here identifies as a soil scientist? Just raise your arms. And who here identifies as a soil health advocate? Perfect, almost all of you, very nice. I want to talk today about MRV with remote sensing for building soil organic carbon, and through that also soil health, and to look a little bit at the opportunities and limitations with this technology. I want to walk through the why, how it works, how we ensure scientific rigor, while also building up economic viability of these solutions, and to talk about the clarity and accessibility. First of all, why MRV? And that's the question why I asked you why you would consider yourself to be a soil health advocate. Because as I followed here the presentations and the talks from different members of the soil health advocacy community, I got the notion that everything's fine. We're well on track. Everything's working perfectly. But when we compare to the ambitions that the 4 per 1000 initiative originally set itself, I think we're not quite there yet. We still have a long way to go. Maybe this original ambition is also not the one that we're still aiming for. We know by now that, of course, we need to reduce all our emissions so that we really get to net zero. But then even beyond that, we will have to additionally take out carbon out of the atmosphere, and that's really where the soil carbon solutions can come in. But I do want to call out this original ambition that the 4 per 1000 initiative had to really pull out a lot of carbon out of the atmosphere and to really create this win-win-win solution with building up soil carbon. And I think this is a great ambition, and we shouldn't give up on the ambition. We should still have this ambition, even though nowadays it doesn't mean to offset fossil fuels, but it will mean to additionally take out carbon from the atmosphere. So why use MRV for remote sensing? We like to look at this as having three pillars. On the one hand, we need to have with our MRV systems, we need to have scientific rigor. We need to make sure that we measure what matters. And I want to thank Axel Don for putting so much clarity on this in his presentation yesterday, that soil carbon really is one of, if not the pivotal metric to really measure soil health. And so I think this is really core, and this is why we come here together. And let's not divert attention. Let's start with soil carbon. We have the methods in place. Let's start with measuring that, and then we can build up on that. Then we also need to build systems that are sustainable. And to make them sustainable, we need to make them economically attractive for the stakeholders that are in these systems. So the farmers, the project developers that are working to build up soil organic carbon, they need to have these economic incentives, and they must be based on the outcomes. So we need this outcome-based financing instruments. And finally, we need the pillar of clarity and accessibility, so that essentially all the farmers, all the land managers can participate and can take advantage of these systems. Now, why should we opt for MRV, for remote sensing as an MRV technology? As Bruno pointed out, just relying on soil samples is just way too expensive. But I think it's also very important to call out that it is the trusted foundation for all other technologies. If we use process-based modeling, if we use remote sensing, if we use other sensors, we must rely on the soil samples. And Bruno, you just shed some doubt on whether we can actually rely on these soil samples and how reliable they are. And I think we all have to agree that they are reliable. I think a measure of sending 36 soil samples to a lab and then comparing them, that's not a true representation of what's actually happening. The projects that we're looking at in the voluntary carbon market, they take thousands of soil samples and then they send them to the laboratories. And what we truly need to evaluate is whether sending thousands of soil samples and then looking at stock changes, is that reliably being measured by the labs? And that's what we need to have trust in. And I invite all the scientists, which I identified earlier, to carry out such studies. They are truly important to understand, can we really trust the spaces? And I believe we can and we must. However, it is expensive. We need to bring down the costs, of course. Now, the process-based models that Bruno presented, they are a great way of scaling, of allowing for this economic viability. But the question are they really fit for the purpose for the carbon markets to truly quantify soil carbon? And I think we're still in a situation where we see an imbalance. We have a lot of research plots. We have a lot of control tests that are not necessarily representative of real-life agriculture. And that is still the big gap that we're seeing. The process-based models, they are being built up on these control plots where researchers, they tend to their control plots maybe like pets, whereas farmers in the real world, they tend to their fields like cattle. And that's the difference. If you're a researcher, you can dedicate a lot of time to really implement the practices in the right way. And then, of course, we have publication bias. So only the experiments which usually have significant positive changes really get published. So we have this representation problem that we understand the mechanisms very well in the control plots, but not necessarily at scale when we look at country scale implementation of these practices. But now with voluntary carbon market programs, we see more and more of these large-scale efforts coming to fruition, and soon we will have first data to tell you about the changes. So looking at remote sensing, the big question is, first of all, from a scientific perspective, is it trustworthy? What about the accuracy? What about the precision? Can it really deliver on the promise of delivering economics at scale? So what's it worth in the bottom line? Can farmers be attracted to use this? Can project developers be attracted to use this? And then finally, is it accessible? Will it be possible to use it for everyone? So looking at how it actually works. When we talk about remote sensing, we often talk about drones, planes, but the most commonly used is actually satellite imagery. And here we see the European Space Agency satellite Sentinel-2 that is taking imagery every 5 days of every spot in the world. Then on the right-hand side, we have the ground-measured samples. As I said, they are the foundation. We must be able to rely on them. And then we can build AI and machine learning models. If we are unsure whether we can rely on the ground-measured data, we shouldn't do ML. Garbage in, garbage out. But when we can rely on them, then we can truly build these models and work with them. So from the satellite imagery, what do they record? They take images from all of the electromagnetic spectrum. So they have not just the visible light that we humans can see, but they can also record infrared radiation. And that is very important because there is a strong signal from the shortwave infrared radiation of soil, of different soil properties, and the near infrared radiation of the vegetation. And both play a crucial role. Okay. So here we can see with an eye that soil has different colors. We've seen this before. This can, of course, also be observed by the satellite. But now let's see. Typically, we often have fields that are covered with vegetation. So how can the satellite actually look under this? Well, we can wait until the harvest is done, and then we can see how the bare soil looks. Of course, over time, we want to see less bare fields, and we want to see more cover cropping. So we will have to get on with being able to tell more from the plant-covered fields. But just looking at this, on the right-hand side, or for you it's the left-hand side, where do we have the high SOC? Where's the high soil organic carbon? Just with the eye test. What would you say? Any idea? Center. In the center, it's the high organic SOC. Why? Darker. It's darker. That's actually true. Yeah? So here we have a very high densely sampled plot. These are all sample points. And so you can even with an eye, in this case, discern where there's higher SOC and where not. And in this case, the remote sensing model can also do this quite well. When we see here, we see that the samples and the remote sensing model fit quite well. Now the question is, typically we have not so high a density sampled field, and the question is, can we still trust the remote sensing based model? So in this scenario where we have way less samples, would you still say we can trust the remote sensing based model? Maybe, yeah, there still seems to be a good fit. What about in this case? Maybe not. This is where we are today at scale. So we need to transition, and again, big call out to all the soil scientists who identified earlier, we need more of these highly densely sampled fields in order to validate these models and to show how well they fit. But of course, there's more than the eye test. There are also numbers. Here we can actually see the distribution in the back. The blue one is the prediction from the remote sensing-based model, and in the front you see the green samples. I just put this here to show that even more complex distributions, like we see in this field, can be accurately modeled. We can talk about the numbers, but I see that I'm running out of time, so I want to come to the other conclusions. What does it mean in practice? Can we make it economically attractive? And this is what we're working on in the realm of the voluntary carbon market. So there's one gold standard project that we've been working on with Gallego and South Pole, where we have applied this. And actually my colleague Ahmad is here, who also has a poster about this specific technology, which is model-assisted estimation using samples and models together. And with that, we can actually save the client, in this case, millions in terms of uncertainty deductions. Here is another example where we worked with our partner Danone. This is an insetting project where we have used remote sensing technology to reduce the effort of soil samples that are required, and we're able to achieve a saving of 450,000 in 1 year. So these are the types of economic attractiveness that we need to communicate to convince more people to start SOC projects and to choose the measurement technology that's good for them. Now, how do we make it clear and accessible? We're really happy to also see representation from Vera here today, as they have recently launched the VT0014 methodology, which allows for using remote sensing in the voluntary carbon market. Also, together with the gold standard, we have published a methodology to be able to use this in practice. And now the technologies are in place. It's just a question of, can we roll it out? We know more capacity building is needed. That's what we want to help out with. Also on the European level, where CRCF is coming, and we're in conversations with the Commission. But I invite all of you to go out, spread the word, talk to us if you have any questions, and let's really get from words to action to build up soil organic carbon. Thank you all.
All right, thank you, Julian. That was a great discussion on remote sensing. So since we started our journey, we started pretty high in the sky. So we started with modeling, then we went on remote sensing. Next stop in this train station will be closer to proximal sensing. So we'll hear about Dr. Polina Rejevics, postdoctoral researcher, Department of Forest Science Ecosystem Processes at the University of Helsinki in Finland. She's going to talk about proximal sensing-based MRVs for carbon farming purposes.
Okay, so I'm Paulina, and as mentioned, I'm the research coordinator and a postdoc at the University of Helsinki. I usually work with forest plants and research infrastructures, but today I represent Project Preable, where I lead the focus group working on proximal sensing in carbon farming. And today I will be talking about carbon farming in the European policy, and in particular the role of proximal sensing technologies in MRVs. In the face of accelerating climate change, the agricultural sector is increasingly recognized not only as a source of greenhouse gas emissions, but also as a key player in climate mitigation. Carbon farming is a set of agricultural practices that emphasizes capturing and storing atmospheric carbon in soils and vegetation, of course, through land management strategies. It plays a pivotal role in climate change mitigation, as this enhanced soil carbon sequestration can contribute to lowering the atmospheric CO2 levels, improving also the soil health and the biodiversity, and promoting sustainable agriculture at the same time. Carbon farming includes practices such as cover cropping, no-till farming, agroforestry, and rational grazing. The effective implementation of carbon farming in the EU relies heavily on robust MRV systems to track and validate the carbon sequestration efforts of farmers and different land managers. A major challenge in carbon farming lies in accurately and cost-effectively monitoring the soil organic carbon stocks at both the field and the landscape level. And in the EU policies, especially through the CAP, we emphasize the need for MRV systems that can reliably measure carbon sequestration outcomes. The MRV ensures that carbon sequestration practices are transparent, measurable, and credible, forming the basis for issuing carbon credits and assessing climate-related subsidies. The European Commission has recognized the need for standardized MRV frameworks as part of its 2023 proposal for a carbon removal certification framework, or CRCF, which aims to harmonize methodologies across all the member states. And now, proximal sensing is increasingly recognized as a valuable tool in the context of EU climate and agricultural policy. It is directly, or at least indirectly, referenced in key EU policies, including the European Soil Strategy and the Carbon Farming Initiative, as part of integrated approach to improve MRV systems. Proximal sensing technologies, which include using instruments like soil sensors or portable spectrometers, are viewed as a potential solution to improve data collection, enhancing the accuracy, low cost efficiency, and resolution of SOC measurements, and supporting large-scale monitoring efforts. By enabling high-resolution on-site data collection, proximal sensing technologies can reduce the reliance on the mentioned before expensive and time-consuming laboratory analysis, while also providing more consistent data sets for long-term monitoring. This is particularly relevant for carbon farming, where reliable quantification of carbon sequestration is essential for verifying the reductions of the emissions, issuing the carbon credits, and maintaining the environmental integrity. Such technologies also support the EU broader sustainability objectives by contributing to soil health, monitoring, precision agriculture, and adaptive land management practices. Now, a range of technologies is employed in MRV, including the remote sensing, as we have seen, and traditional soil sampling that was mentioned, and for example, UAVs and drones. And each of these tools contribute valuable insight. They also present notable limitations that hinders the scalability, accuracy, and real-time monitoring. So the conventional soil sampling and laboratory analysis remain and will remain the gold standard for SOC measurements, as it provides highly accurate ground truth data that we have to trust, as we've heard before. Despite its accuracy, this approach is resource intensive. It requires significant time, labor, and financial investment. The need for the repeated sampling to ensure the accuracy increases the cost and reduces the visibility for widespread ongoing use, large-scale carbon farming operations. On the other hand, remote sensing technologies such as satellite imagery or drones are highly effective in providing large-scale coverage, but they are largely limited to the surface-level observation and struggle to capture the below-ground processes such as SOC accumulation. These limitations highlight several gaps and challenges in the current MRV technologies. So here is where the proximal sensing is coming as valuable. Unlike the remote sensing methods, The proximal sensing provides a connection between, with the soil, enabling more accurate and localized assessments. Proximal sensing can also offer real-time data collection, enabling continuous monitoring of SOC and carbon sequestration activities. At the same time, the proximal sensing technologies can offer cost-effective solutions, reducing the need for the labor-intensive soil sampling and lab analysis. As carbon farming scales up across diverse agricultural landscapes in Europe and elsewhere, the integration of proximal sensing into MRV frameworks could enhance the credibility and transparency of carbon sequestration claims, then support the certification of carbon credits, and ultimately contribute to achieving the EU climate and soil health goals. Now, a wide array of proximal sensing is currently available or are under development, and different technologies operate differently, providing unique insight into soil characteristics. As part of the Credible project, we have created a comparison survey for proximal sensing technologies that aim to be used in carbon farming. And this table is very dense, and I will not go into details of each of these technologies. And in a second, Chris will talk a bit more about the practicalities. But this document with the table is available online on the Credible project websites under Public Consultation tab, so you are welcome to take a look. Proximal sensing technologies, as mentioned, offer several significant advantages, improving MRV system in the context of carbon farming. One of the primary benefits is the capacity to deliver high spatial resolution, allowing for detailed and site-specific measurements of SOC. Fine resolution data provide farmers and stakeholders with timely insight into carbon dynamic, which are critical for tailoring land management practices to site-specific conditions, so enhancing the effectiveness of carbon sequestration strategies. Another key advantage is the cost effectiveness. And of course, the initial investment in hardware and calibration is required, but then the technologies can significantly reduce the need for repeated manual soil sampling, laboratory analysis, and field labor in a long-term perspective. Proximal sensing are also adaptable to different soil types and conditions, provided, of course, that they are properly calibrated. And despite the significant potential, proximal sensing the techniques of course have several crucial challenges that must be addressed to fully harness the benefits within the MRV system for carbon farming. One of the primary limitations is the need for robust calibration. Proximal sensing, especially those relying on spectral principles, must be calibrated against traditional laboratory-based measurements of SOC to ensure their accuracy and reliability. A further complication arises from the volume and complexity of the data generated by proximal sensing systems. High-resolution continuous data collection, this is very valuable, but can produce vast datasets that require substantial computational resources, storage capacities, and advanced data processing algorithms. Then interpreting the data usually involves machine learning, which demands specialized expertise and infrastructure. Last but not least, we have to remember that it's not us, the scientists or politicians, whom we need to convince that proximal sensing or carbon farming per se makes sense. The farmers or land managers are the ones who will or will not use the new technologies and will or will not engage in carbon farming practices. So as part of our work in the Credible project, we also look at the more sociological aspect of carbon farming, and specifically proximal sensing and proximal sensing related digitalization, considering farmers' technology acceptance and transformative capacities. Now, all of these challenges highlight the need for continued methodological development, including standardization of calibration protocols, improved soil sensors, and so on, and also to ensure wider adoption of the methodologies. I think we don't have maybe time to go into this, but I will close up with some key messages from my talk today. First, carbon farming is becoming central to the European Union's climate and soil health goals. But its success depends on strong and transparent MRV systems. Proximal sensing has real potential here. It can provide high-resolution, real-time and cost-effective data on soil organic carbon, making the monitoring more frequent and more practical. When we compare it to existing tools, proximal sensing can fill in important gaps. It complements the accuracy of traditional lab sampling and the scale of the remote sensing, while overcoming many of those two methods' major limitations. At the same time, we must not overlook the challenges, including calibration, the issue of soil variability, handling large and complex data sets, and ensuring the farmers' acceptance or land managers' acceptance. And we need solutions in all of these areas. Finally, the role of the EU policy is decisive here by supporting funding, creating more flexible and practical frameworks, and supporting the digitalization and helping farmers in the adaptation. The EU can help scale up proximal sensing and make carbon farming both credible and transformative. So in short, proximal sensing is not a silver bullet at all, but it can be a cornerstone in building trustworthy MRV systems that bring carbon farming into the mainstream of EU climate actions. And finally, as a last slide, I would like to thank to my team of the Credible project, both within my focus group and my work package, and the management team, of course. I encourage you to get familiar with the project activities on our website, and soon we will open registration for our third and final Carbon Farming Summit in Italy in March next year. If you need any more information about the project or the activities of my focus group specifically, please do not hesitate to reach out. I cannot see the clock, so I don't know if I went over time. If yes, sorry, but that was all from my side. Thank you.
All right, thank you, Dr. Rejavics. That was a very great perspective on proximal sensing. Now we'll get a clear example of proximal sensing in action with a company based in Boston that will tell us a little bit more about what is proximal sensing really doing in the scheme of carbon, voluntary carbon markets. So Mr. Chris Stollis will come to the stage, the CEO of Yardstick PBC. So he'll talk about in situ spectroscopy for low-cost, high-rigor soil organic carbon MRV at scale.
Thank you. So first, my 4-year-old heard that I was giving this presentation, and she was like, Daddy's going to be on a stage. So I promised we would get a photo to prove to her that, yeah, I'm actually on a stage. It's pretty cool. Okay, thank you. Great. Next, ostensibly are my slides.
They are on.
You're doing great, Lance. Well, I know what the first slide says. It says I have 2 disclaimers first. The first is this is almost exclusively an American perspective. Almost all of our work is done in the States. So some of what I have to share may be completely wrong in your context, but that's why I'm here, to learn from your experience as well as share mine. And the second, for shorthand, I'm going to talk about soil carbon measurement or soil CMRV. People use these words to mean completely different things, and that is unhelpful. So for the sake of my presentation, I'm going to focus very narrowly on soil organic carbon stock quantification. There are my 2 disclaimers. Okay, disclaimers made. So, 4 things I want to talk to you about. What we are big picture, our geoderma paper, some more detail on fit of curve, and then I forgot to take out number 4. I'm actually not going to talk about sample prep. It's from the same even 2024 paper that Bruno mentioned, but it makes lab quantification really scary and hard. And sorry, that's a mistake. I'm not going to talk about that. This is an oversimplification. I am a recovering management consultant, so things need to be on a 2x2. The x-axis here is accuracy. The y-axis is cost. Right now, we have two buckets of technologies that we've heard about. Bottom right is laboratory analysis, mostly combustion. Top left is biogeochemical modeling of soil organic carbon. These are really important technologies, both of them critical. Nonetheless, there is a gap here in cost and accuracy trade-off. Yardstick is not an alternative to these technologies. As you'll see in a minute, we rely on combustion analysis for training, and our customers are often biogeochemical modeling service providers. Nonetheless, in sort of like the constellation of things, where I want you to think us living is more affordable than laboratory analysis while maintaining scientific rigor, and more accurate than, understandably, high uncertainty, long distance quantification via remote sensing or other geocovariates. This is the feedback loop that we're trying to break. I don't have to lecture this group about why measurement is important. We have a broken feedback loop where the externalities of all of our agricultural systems are very slowly starting to reveal themselves, or not slowly starting to reveal themselves, and that's really bad. What we want to do, not by ourselves, but I'm giving the presentation, so it's our logo in the middle there, is interrupt this bad feedback loop with better measurements so that we can understand what's going on well, so that we can prioritize practices that address the calories need we have, right? Regenerative solutions that reduce calories like does not work for the world, and at the same time, we got to reduce emissions, improve soil health, improve supply chain resiliency, et cetera. I'm going to show you a video in a moment of this thing on the left, which is the technology that we're most well known for. We focus on Vis and IR reflectance spectroscopy for soil carbon stock quantification as an alternative or a complement to laboratory analysis. But what we do on your right there is a bunch of other stuff. So we do sample planning, we do the field work, we're a service provider. Our customers hire us to do the work. And therefore, there's Internet of Things as well that I'll show you in a moment. I'm going to click this, and you're going to see what it looks like. Oh no, maybe I'm not going to click it. What happens if I click? Does anyone speak that language? Enter. Okay. All right, whatever. I'll send you a link if you want. It's a big-ass hand drill, right? So you can see at the top there is a hand drill. When you pull the trigger, it starts drilling down into the soil. So at the tip of the probe, right there, there's a sapphire lens. We're shining light out of the window. It reflects off the soil. Once the probe is underground, that soil is pressed very tightly up against the lens. That light bounces off the soil, back into that same lens. There's fiber optic through the shaft, and then there are spectrometers and other gizmos in the hilt there, the white thing, that would be spinning if the video were working. But it's not, which also means now my clicker won't work either. We are derailed. Oh dear, Lons. I'm sorry. So this is happening in field. As you can see, there's a person holding this instrument. This data is collected in field. Right now, we don't typically put our models on the instrument because real-time results is not valuable to our customers. But the point is, with good science that I think we are increasingly doing, we are using that instrument for quantification of soil carbon instead of or as a complement to combustion analysis. I don't know what the next slide is, so I can't get ahead of it. There we go. So this is what our results look like. We deliver stock reports to our customers. This is, congratulations, you have 21,000 tons of organic carbon in your make-believe farm in Minnesota, I think this is. That's what we get hired for. Hey, Yardstick, I want soil organic carbon stocks quantified on my 10,000 acres, my 500,000 acres, whatever it is. This is our actual deliverable, and we're increasingly delivering this with spectral technology, though a lot of our work is also conventional because our technology is not suitable in every land use context. This is a cutaway of the instrument, so I already talked you through this in general. That right there, illumination lamp, shines out the sapphire lens, bounces off the soil, back down to the collection mirror, up the mixing fiber. The mixing fiber goes up to the probe hilt where there are spectrometers and other things. So we're basically taking a real-time spectral movie of the soil profile. As we're drilling down into the soil, continuously, we're recording spectral data along the full 45 centimeters of the soil profile. We also have a 1 meter instrument in development, but most of our work is to 45 centimeters. This is the web platform. Of course, we're doing all the same metadata for traceability, chain of custody, where were you, expected versus actual, and there's really cool features to connect our in-field behavior to the instrument. So our teams scan the probe itself to provide a real-time, actual moment in time where we're confident that things are in the same place. Okay, we published a paper in December in Geoderma. We were very proud of this. It was miserably difficult and long, but now it's here, and no one can take it away from us, and getting through the gauntlet was really fulfilling. My perspective is that anything working in nature-based solutions, whether it's the voluntary carbon market or other economic levers, absolutely must lead with science. If you do not publish, I don't think you deserve to be in the room. This is critically important for the long-term viabilities of these markets. We have seen over and over again from avoided conversion in forestry what happens when mediocre science continues for years or decades before The Guardian catches up or Newsweek catches up. So while this paper by no means establishes, like, oh, yardstick is good to go, rely on it for anything, it's an incredibly important and super unique milestone for us that we're proud of. And it also, super importantly, included our scientific collaborators at the Soil Health Institute. We are on site collecting calibration cores. So we collect a 45 centimeter calibration core that's sliced into 5 centimeter sections. We're collecting spectral data immediately adjacent. We receive laboratory data back on the calibration cores, and then we're paired by depth. So the bumps on the side of the probe are measuring depth in real time. That's how we associate a given piece of 5 centimeter depth lab data with a given set of spectra, which remember are continuous as we go down. Then you put the model to the spectra. I try and avoid the word modeling because it makes it confusing with the Bruno Basso world of modeling, but nonetheless, these are machine learning techniques. There is a model that's using spectra to understand soil organic carbon. This is figure 12 from the paper. I don't have time to go through the paper right now. The point is, we're really pleased, very high accuracy. We believe this is the most accurate in situ Vis-NIR spectroscopy data for soil carbon ever. It is not perfect. There is so far to go. This is one land use context in Illinois. There are so many caveats that are really important to make, but nonetheless, we are very, very proud of this data, and we think it's unmatched. We have fancy customers. These are folks that span the voluntary carbon market, Scope 3 programs. We also have land funds that are customers that want to quantify soil organic carbon to understand the value of the capital asset, the farmland that they've purchased and are managing differently. Our revenue is dominantly the voluntary carbon marketplace, and that is a liability for all the reasons we know that the VCM is an imperfect tool. So Yardstick is in the business of measuring soil carbon so we can preserve and restore this unbelievably important asset. If it's the VCM that makes that possible, great. If it's CRCF that makes it possible, if it's CBAM, if it's whatever, nature restoration law, we don't care. We are economics agnostic. We just want there to be economics that make these management practices viable. And we have cool investors. The reason I put this up here is because I like that the carbon buying world of Microsoft and the nature conservation world of TNC are united in their conviction that measurement of soil organic carbon stocks is unbelievably important. Single largest terrestrial carbon stock in the world. We're messing it up. If we're going to stop messing it up, the slogan we got from SHI is measure what you treasure. Like what gets managed, what gets measured gets managed. We are firmly committed to outcomes-based economics because we want to focus on the things that we're actually trying to achieve. We've done this all across the US, over 1 million acres, 40 states. We've done work in Mexico and Australia as well. We do not have an international strategy. We just go where the money is. So if you're a customer and you have money, I would be glad to measure your soil carbon in Germany or anywhere else. But nonetheless, we've tried to stay focused on our home market of the US to make sure that the technology is mature before we take on the additional complexity of OUS work. All right, last thing to share, fit of curve. So our Geoderma paper talked about point stocks. These are stocks to 30 centimeters at individual sample sites. Since that, the Geoderma paper was published in December, and the field work for that paper was spring 2023. So we are loads past that level of sophistication. We have not yet published this, but we will. This is about taking that that math from the sample site level and bringing it up to the stock level, the project stock level. So I have two examples to show you here. The x-axis is stock in tons. The y-axis is probability. All high-quality, good data science stocks are a probabilistic distribution. In this case, we're overlaying a conventional stock in blue, which is combustion data, with a probe stock, spectral, from Yardstick's technology in gold. In this case, we're using the technique in a Geoderma paper, which is called model to stock. You'll see at the top there. And what that means is we do not have independent concentration and bulk density values. We're modeling directly to stock. You can read the paper if you want to know more about that. It's kind of controversial. It sort of blows a lot of soil scientists' mind that you would not have concentration and bulk density values, but we think there's a lot of potential in this approach. Nonetheless, I also want to show you one that incorporates ESM, which I agree with Bruno is important, so long as we fix bulk density quantification at the lab. This is from a totally different scale, totally different geography, totally different customer. And in this case, we're modeling the concentration. So sometimes there are good reasons for us to want an independent bulk density value. In that case, we're quantifying bulk density conventionally. So we're measuring carbon concentration spectrally, and at the same time taking a physical soil sample for bulk density. The point is that these curves like materially overlap. They don't perfectly overlap. And so I would actually respectfully disagree with Paulina's point about the accuracy and maturity of laboratory data. I think laboratory data is not a gold standard. It is actually like deeply troubled and conflicted. This analysis presumes that this laboratory data for reference has zero error. And that is not true. Laboratory data has error. We just ignore it a lot of the time. And that is bad science. It also disadvantages my technology. So of course, I'm inclined to get us to agree that laboratory data could get better. But nonetheless, we believe this is an understatement of our performance because it falsely assumes zero error in the comparison lab values. That's it. Thank you. Thank you.
All right, thank you, Chris. That was good information on the state of proximal sensing. So as you can see, there's already mature technology that exists out there in the market quantifying organic carbon at scale. So next up, we will hear about Dr. Marcus Shidung and Dr. Laura Sophie Arbo from Tunun Institute for Climate Smart Agriculture. I hope the wording of that was right. So they're going to talk about the changes in soil organic carbon in Germany and Europe, the results from repeated inventories at national and regional scales.
Yeah, is it working? Yeah, okay. Thank you. So we are from the Tunun Institute, so we will present some ground truth data. So we are the people who are going out and take the samples and measure them in the lab, and actually not we personally, but our institute, and we analyze the data. So I will start with presenting changes in Germany, and Laura will continue with some drivers we expect to explain these changes, and then also talking about changes across Europe. So let's start with the German agricultural soil inventory, so the Bodenzustandserhebung Landwirtschaft, which we are in charge of at the institute. And the first one, Axel also talked about it yesterday, took place between 2011 and 2018. So we have a 8x8 kilometer grid across Germany, which you see here on this map. This includes all cropland, grasslands, and permanent crops within this grid. So we talk about 3,000 sites. Farmers take part of this voluntarily, which works pretty well. And we also have farmer questionnaires to get some data from farm management and so on. So the first inventory, which also Axel showed yesterday, was there to actually quantify how much carbon is in the soils of the different land uses. So we see here that croplands have less than grasslands, and permanent crops are in between those in the first meter of the soils. And then we have the organic soils, which are very high in carbon stocks, which we not focus on today because we separated the organic soils from the mineral soils internally. So we have a group working on organic soils where Bärbel Thiemeyer, who's also around, is in charge of, because of the differences in sampling and handling samples from organic soils and mineral soils. So we focus on the mineral soils today, and we are currently in the resampling of the German agricultural soil inventory. So this is our current status. We have, after 10 to 12 years, this is the interval we are looking for specific sites, sampled around 1,200 sites, and roughly 1,000 are analyzed. We look at the first half meter of all of these soils. And the sampling design looks like this, that we have our central point where we took the initial sample, and then we have a grid around it by 12 meters. And you see the boxes with the 2. So this is where we are right now. And then continue 3, 4, 5 to 9. So we are kind of prepared for 9 further inventories and hope for the money to do this. So what we can present today is the change of approximately 600 sites from the course of the first inventory around this grid, where we can compare the data and also look at the variability, which was a quite important topic already before. So to just give you an impression, we have our own laboratories built for the inventory. So this is the infrastructure we have. You see our laboratory on the top and our archive at the bottom. We do analytical measurements of nitrogen, of carbon, and everything we need for carbon stocks. So all the bulk density, rock fragments, and fine soil mass. We look at roots, texture, and other parameters. which you see here in the list. And what we added for the second inventory now is looking at aggregate stability and air capacity as potential parameters for soil health indicators. And we also started to implement mid-infrared spectroscopy, so building up a national-wide soil spectral library, which is actually the part where I'm mainly in charge of, to building up this library, using the library for predictions, and so on in mid-infrared. What we also get is the management data, which I mentioned. So this is based on questionnaires, and we do also gap filling of data we miss from other products to fill the data. So we ask for crop types, yields, fertilization, liming, tillage, and all the different farmer practices. So this is in a different quality depending on the farmer, but basically it works pretty well, but it's very difficult data to handle because you need to kind of normalize it, harmonize it, and so on. And we have this for the 10 years before the first inventory and all the years between the first and the second inventory, or the resampling. So we kind of have a 20 years coverage of management data for most of our sites. And we talked about variability. And this is a variability we have to deal with. There are surprisingly little soil photos in this in the conference, I feel, so I put a few here. So this is the variability we have to work with in the field. These are photos from our field scientists who go out. So you see, it's pretty challenging to take representative samples of this, and we talked about this. And we have also big challenges with this, even though we have our own lab, own protocols, and use the same procedures over the initial and the resampling. But it works, so we get some carbon stocks. This is just the carbon stocks of our second inventory. So we see quite similar pattern here between the first and the second one. And we will mainly focus on the cropland and the grassland, because you see we have just a few sites so far from the permanent crops, which are in general very little in the whole data set. But the most interesting is now to look at the changes, so the ground truth changes, the analytical measured changes here. And we see on the scale we have right now for the 600 sites that we have losses in croplands and grasslands. So you see here the data spread is pretty wide. And we have so far little gains in the first 10 centimeters of croplands. But when we look at the 30 centimeters, we see that over the whole time period we have 1 ton of carbon loss in croplands, which is 2% of the carbon stock, and 5 tons of carbon loss, which is 6% of the carbon stock in grassland in the first 30 centimeters on the national scale. And this is based on 600 samples, so this is not representative for the whole country yet, so it's really the first results. And a way to look at the data in a different way is to rank it according to losses and gains, and which shows us the magnitude of loss and the share of losses or gaining sites. So this is what you see here. So this is just ranking high loss to high gain of croplands and grassland. And what this shows us is, first of all, the rate. And sorry for this, we miss a year here in the unit. So these are the rates. So we have 0.04 tons of carbon per hectare per year, which are lost in croplands. And we have 0.3 tons per hectare and per year in the grassland and 0 to 30 centimeters. So quite substantial losses, especially in the grasslands. And what we also can see here is the distribution of the losses. So for the croplands, we see we have 50-50 more or less. So half of the sites gaining, half of the sites are losing. And for the grasslands, we have substantially more sites on the left, so sites which are losing substantially. And more important, the rates of losses are higher. So you see the red bars in both cases, more extreme in the grasslands, are higher than the blue bars. So this explaining these losses. So we have these substantial losses and more sites that lose, and when they lose more than the sites that are gaining carbon. And we think about what the session is about, MRV, and accounting for carbon increases. I want to go back to a figure from Axel's paper, where we have the different concepts of the baseline, and in the top we actually have concepts where we have carbon sequestration, But looking at our national inventory data, it's more that we shift from sequestration to loss mitigation. So we need concepts which actually account for this losing trend we see on the national scale. And then we're more here with the blue arrow, so the measures that mitigate the losses rather than additional sequestration on this large scale, on the national scale in Germany for the sites we have so far. And the sites we have so far is not evenly distributed, so I'm a little bit careful of saying this is a national trend. This is a trend we have right now. But what we can say, and we don't go into separating this into regional scales and so on, we have areas which have high carbon stocks, they also lose. So we have this legacy most likely in some places, for example, in the north of Lower Saxony, in the northwestern part, where we have soils which have a high carbon content, which are under water influence, for example, and they lose a lot of carbon. And this brings me to more drivers analysis, and I give the stage to Laura for this. Yes.
Hi, I'm Laura Harbo, and I'm also a researcher at the Thünen Institute alongside Markus. And what I do is that I do a lot of the statistics for the national inventory, and I also look at drivers and how to explain the changes that we're seeing. This work is, as you can see, ongoing. We only have parts of Germany sampled, and we are also still collecting the data from the farmers. So overall, we're not able to do definitive analyses yet, but our preliminary analysis is that we're looking in large part at the influence of climate. We know that Germany has undergone quite a lot of warming recently. Since the last inventory, it's actually about 0.2 degrees per year. It's a lot. So we're looking at how much can global climate change explain of soil losses, soil carbon losses, and this is a study by Christopher and Axel that shows that over 100 years, about 4% of the carbon losses globally in CO2 30 centimeters can be explained by the climate. And this is also approximately in the range that we're seeing the losses in the inventory. So these match very well. This is for the temperate zone, annual losses of 100 years, align very well with the range of change per year that we see in the national inventory. However, our range is also higher, so there's probably also an influence of management. But we're looking at how to quantify the influence of climate in our network. As I said, we've seen quite a heating. This figure shows the annual climatic water balance, because we're also looking at the influence of water and drought or less wet conditions on our soils. However, this is still work in progress, but we believe that at least part of the drivers are to be found in these difficult to manage climatic aspects. Furthermore, we're also looking at management effects, for example, fertilization rates, influence of tillage, liming, cover crops, land use changes, and historical land use. We are also seeing that there is likely a lot of losses in soils that are heavily water influenced with high groundwater level, so perhaps there is also an oxidation influence. But this is ongoing analysis, so unfortunately we don't have anything conclusive to share with you today. However, we are always looking to understand our changes, our results in the context of Europe and what other people are finding. So I've done a bigger review of soil monitoring networks in Europe, where we have repeated monitoring networks. And I found 16 countries and regions in Europe that have been covered by national or regional soil monitoring networks with more than one sampling campaign. When you have more than one campaign, you can calculate the change, for example, in carbon content or carbon stock. And the data actually goes back really far to the 1950s. In Belgium, we have data. Most of the data in Europe is actually collected from the 1990s onwards. And the data that is the newest, perhaps in the past 5 to 10 years, is likely not published yet because it does take a while to resample. So this is just a timeline of when the data is available. Just to tell you that, of course, carbon changes in the soil can be quantified both in content and in stock and in relative changes. So I'm going to go over different versions depending on what other researchers have chosen to publish, because they're not directly comparable. Also, the sampling depth varies between countries. doing comparison with other people's work is very complicated. So we're basically limited to the topsoil, undefined, because everyone does it differently. And it's the same with land use. No country in Europe seems to be 100% agree with each other on what is agricultural land. So we have to go with the definition that the researchers themselves have used. This figure shows the carbon stocks that have been reported from repeated monitoring networks across Europe. The dashed lines are shown to be non-significant, and the pink country here is Germany, our preliminary results. And we see that generally Germany is at the same level as other countries that have reported carbon stocks at the national or regional level. And if you look at the carbon stock change per year, it's also very comparable. We see losses in croplands in all three depths, but these are not statistically significant. We're also still working on figuring out the best way to do the statistics, which is ongoing work. But we see Germany here lies within the range of the other countries that we've been able to find, both for cropland and for grassland. Notably, grassland has quite also losses, like we find, but none of the found changes for grasslands in Europe have been statistically significant. So I would also like to note that often people don't say whether or not they tested their changes statistically, so we don't know. But so the ones that are not dashed are either they said they were statistically significant, or we have to assume that nobody would publish non-significant work without saying. So yeah, Germany is quite normal when it comes to carbon stock. When we look at carbon content, Germany is also in the same range as many of the other countries. Maybe more interestingly, we're also very much in the middle when it comes to change rates. So overall, we do see losses for large parts of Europe over time. Of course, there are also increases. I feel like when I've been listening today, there's been a sense of we're going in the right way. I don't see that in my work, but this is also, of course, biased towards the countries that have repeated monitoring networks. Many places don't. I think I have some numbers coming up later, but large parts of European croplands is not currently covered by repeated monitoring networks that are not LUCAS. So it's truly hard to say how the current level is. And then, relative change. I'm just looking for ways to compare the data. Germany is also very normal compared to the other countries. And we once again see frequent losses. I've mapped it for you. Blue changes are negative, greens are positive. Of course, the whole country is covered, and not just the area where the specific land uses are found. So it might look better or worse depending on the distribution. But overall, we see both increases and losses in carbon across Europe for both land uses, and there is no one direction. And things are more complicated than just these monitoring networks are able to capture. Of course, we're aware that LUCAS soil exists, and I have the figure here to show that they say that in 0 to 20 centimeters, there is a loss of crop from grasslands and croplands across Europe. In our approximately same time period, we see a similar loss in carbon stock for the BID-ZE as well. So we haven't been able to get the LUCAS specific data for Germany, but overall it looks very similar. And we even see that the map here, the blue region for Germany, they predict losses, which we also find. So there's a good agreement, at least with the data we currently have. So when it comes to coverage of soil monitoring networks in Europe, only 29% of croplands and 18% of grasslands are covered by repeated monitoring networks. A larger proportion are covered by a single observation, a single sampling campaign. But we need multiple campaigns to be able to do changes and trends in time. Germany covers about 11% of croplands and 9% of grasslands in the EU, UK, and Switzerland together, the area, which means that by the time we are done sampling, this will be boosted by quite a bit. France is also currently undertaking their second sampling campaign, and they also have approximately the same area. So a quarter of European croplands and grasslands will be covered, hopefully, in like 5 years, which is soon in carbon times. Of the data that we have available, 12% of the area of cropland gain carbon, where 15% lose, so it's quite balanced, which fits well with the data that Markus presents. But 70% of the area in Europe is not currently assessed with national reporting. Grasslands, we see much more losses at 12% of the area versus 3% that gain. But yeah, 76% are not currently assessed. So there are large parts of Europe where, at least nationally, there is not good monitoring. So the conclusion of our talk today is that we see carbon losses in croplands and grasslands in Germany, but much more in grasslands. Germany, the changes in Germany are similar to the European changes, and the drivers are still under assessment, so you'll have to come back whenever we do a presentation. But we're looking at climate attribution, management attribution, and pedogenic attribution as well. Thank you.
Either way.
Yeah. Can you hear me? Okay. I have a question to Professor Basso and, of course, all of you on the stage. But you mentioned the soil equivalent approach, soil mass equivalent approach, to be obligatory to do a good assessment of soil stock. And Mr. Fowler explained in one of his papers that the mistake of calculation could be up to 17–20%. Now, the question, you have seen so many soil analysis studies. How many of these studies do really consider soil mass equivalent approach? And then the next question to the Thünen Institute is, how many of these assessments in Germany have actually considered a soil mass equivalent approach? Because I can't see any evidence that it has been part of the scientific practice until now, especially when you compare sustainable land management systems or organic farming with conventional farmers, or even use a kind of a model-based baseline modulation. It could be a significant difference, and the impact of sustainable land management could be highly underestimated if this soil mass equivalent is not considered. Would you confirm this?
100%. I strongly confirm that very few people do that, and the level of error in bulk density, because of all basically a different volume that you get in response to increases in organic matter, or even compaction. Compaction could go on the other side. So unfortunately, it's a reality, and that's one of the reasons we invested time in publishing the paper and providing the correction that would allow you to do a better job in quantifying. But otherwise, you could lose basically up to 10 tons again, and that it will be several years of sequestration. But it's very difficult to measure bulk density. That's the reality. When you take it, you know, the time you do it, some people may do erroneously after, not after enough tillage event, or, it's just complicated for sure. And that's why you could use the equivalent soil mass altogether and fix that problem.
All right. Yeah, we'll just
one more additional question.
Yeah, we only have two questions. We only have like 2-3 minutes, so we'll try to. I know there's a lot of enthusiasm in regards to MRV, and I like that from the room. But if there's any questions, I'm sure the panelists will just stay for a coffee. Abby?
Can I answer as well about the ESM? You asked also for Thünen. So for the inventory, we do ESM based, but we don't necessarily do it the way that some of the articles describe. We've chosen the first observation as our reference. So we have a constant reference in time, because if we say do 4 or 5 repetitions and we always choose the lightest mass as the reference, we will keep having less and less soil to compare over time. So we've chosen the first one as a reference. We can talk later if you want to know about the math. I did it, so I can answer all your questions. But we do use the ESM. What typically is said about ESM is that you have to have multiple layers to do ESM, and many of the monitoring networks in Europe only do the topsoil. So they don't have data enough to do ESM as per the typical descriptions. You can cut away, but you cannot add from the layer below. And they also would run into this issue of less and less soil to compare. So they don't typically do it, but in the German inventory, we do ESM. However, we do actually see that the losses got larger when we used ESM. And that is, we think, because we're starting to add more and more subsoil, because we're always adding from the bottom if the layer was too light. So if you have a carbon loss, then you would further add subsoil into the layer above, thereby diluting the observed carbon. So we actually saw that the ESM exaggerated the losses as compared to before. So it's not a fix-all or a consistent effect that it has. That's a good question.
So I have a question regarding what I thought was very important underpinning from this morning's session, which was microbial processes as being a key driver to, let's say, enhance carbon sequestration and the different pools of carbon. But what I'm finding is missing in the MRV landscape currently, process modeling and so on and so forth, is addressing this specifically, right? So how do we, so what is the path forward to incorporate different microbial solutions and also to address these different pools of carbon which are completely missing from the landscape?
Well, the variability on microbial activity is highly spatially variable. So it's really daunting. I think Francesca provided a really good answer this morning, that first we have to understand who lives there, what function they have, what traits, that eventually it's all about proxies, how you capture some of that. But we're still in the beginning. Despite the fact we still are able to understand changes by accounting for the mass of carbon inputs and the different pool sizes, type of pools, and so when the inputs are right, the models could be basically spot on. And we're not necessarily accounting, but we have a labile pool, which is kind of, the fudge factors that will basically account for some of those short-term dynamics or the quantity of microbes chewing on the rest of the pools. So they're not fully captured, but we're not in complete infancy or not be able to model soil carbon. That's really not the case.
I can also add from the commercial perspective, in my world, there's a small number of companies with novel microbial treatments that they want to make soil organic carbon claims about. And invariably, they have found measurement service providers non-existent to help them with those claims. And so all of them have felt their hands forced to develop some of that in-house. That creates a pretty profound conflict of interest, right? The measurement technology that I invented to measure the impact of my own bugs shows that my bugs work great. Is like, all right? So I don't have a good solution for that, except to be pretty dissatisfied that that has been the way their hand has been forced. I will say, though, that some of what he was gesturing towards with dynamic baselines and high quality controls are appropriate. The one company, to my understanding, that's gotten some VM42 momentum has done so by basically treating their microbial treatment as a practice change. And so great, if you can have high quality controls, you may not be able to isolate the causal piece of the culture, but you've got a control and you've got critters, and presumably you can observe the outcomes, even if you might not know much about what's actually going on in the underlying biogeochemistry of it.
All right, so that was the last question that was allotted in terms of time. So I want to thank the 6 panelists that shared a great vision about carbon MRV. No, they'll all be out in the tables there if you have more questions for them. And the next session is starting in 8 minutes, so 3 breakout sessions still. So thank you everyone for your time.
Thanks so much, man. Thank you very much.